Okay, everyone, let's get started. Welcome to lecture 9 of 10 of the Stein's Method Summer School on queuing approximations. At this point, you all know the drill. So please, Anton, take it away. Anton, I think you're muted.
Yes, I was. Thank you. So this is the last week of the course, and I have to say that it went faster than I had originally thought, at least for myself. Maybe it's torture for you guys. Uh, so in this last week, for the past maybe 3 or 4 lectures, we've been going at a very low level details, covering low level details. For the last week, the pace is going to pick up a little bit. The idea being that I want to show you, it's going to be more brisk. I want to show you a couple, like more things and not necessarily cover them in to the full painstaking detail, but just some perhaps reference markers that you can take away and then you can revisit these as needed. But with that being said, there is still going to be some detail. Okay, so last class on Friday, we covered last lecture. We covered the MH2 n plus m model. And we did specifically state space collapse. Now, there was the other reason beyond state space collapse for me showing you this two-dimensional model is today we're going to talk about gradient bounds or again Stein factor bounds for the multi-dimensional setting or dimension d bigger than 1. And the reason this is such an important topic, first of all, this is the main technical driver of any Stein's method application, getting these gradient bounds. And in the one-dimensional case, we have an ODE. The Poisson equation is an ODE, so this one. And we have a closed form solution for it. H of y. We have a closed form solution for it, and we exploit that and kind of brute force our way into the bounds. In multiple dimensions, it's a PDE, partial differential equation. Usually this will be something like sum I goes from 1 to d, bi, so b is the drift vector and bi is the ith component. This is the partial derivative with respect to the ith coordinate, plus 1/2 sum I comma j goes from 1 to d, aij of x, partial I, j, f sub h of x. Okay, so that is the operator. And it is a partial differential equation. And we would be dead in the water, usually, if not for some very special structure, which is perhaps to be expected of diffusion processes. Namely, something about this diffusion matrix. So I'm going to call it diffusion coefficient, diffusion matrix. And most of the time, if we have a non-degenerate, let's call it non-degenerate diffusion on R to the power of D. Non-degenerate is a term that I am using. I don't know that it's necessarily any official term, but what I mean by that is the Brownian motion, which is driving the whole process, is indeed d-dimensional. And another way to state this is that the diffusion coefficient matrix, so square root a11 of x dot 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 a d d of x is, or not the square root, just this matrix is positive definite. Okay, so we're going to be using this structure a lot. And let me dive in right away. The result I want to highlight is by Itai Gurvich, and I want to get you the exact paper. It says diffusion models and steady state approximations for exponentially ergodic Markovian Qs. This paper has a lot of details in it, but today we're going to be talking about specifically theorem 4.1. And instead of just showing you the theorem, I'm going to parse it for you a little bit. I'm going to show you the theorem, meaning write it down instead of just flashing it in front of you. And the reason is it is a very complicated theorem. If you want to be very thorough in understanding it, has a lot of moving pieces. Okay, so let me give it. Okay, so we take omega in RD. So the presumption is that we have this Poisson equation on RD, and it is unrestricted. The domain is not restricted. In other words, it's on the entire domain. And we take this Poisson equation, and we're going to be basically talking about local behavior on subsets of that. So be an open set, and let U be in C2 alpha, be a bounded solution bounded in omega to 1/2 sum ij ai j of x partial I partial j u of x. This is the Poisson equation. And the reason I swapped out notation right now is because I want to stick to Itai's notation in the paper. Okay, so we're used to seeing on the right-hand side of the Poisson equation, we're used to seeing h of x and the solution being f sub h. So here, to stay in the language of the theorem, u is going to be our solution. Hopefully that's not too confusing. Okay, so f is going to be in C alpha for alpha between 0 and 1. Okay, so what is this C2 alpha? The C2 alpha, it's C2 functions, twice continuously differentiable, with alpha holder or alpha holder, I can't say it properly, but alpha holder second derivatives. If you want to think about alpha equals 1, although I have to be explicit, this theorem does not cover the case where alpha equals 1. But if we think about, for just comprehension's sake, C21, this is the C2 functions with Lipschitz continuous second derivatives. And the alpha means alpha holder. Basically, just for completeness, it means that the sup over xy in the set omega of the second order derivative over x minus y to the power of alpha. This is, say, bounded by some constant. Okay, and again, if alpha is equal to 1, then this is basically Lipschitz continuity. All right, and here f F and C alpha means that this is also alpha holder continuous. We're used to dealing with Lipschitz continuous test functions. So if the function is Lipschitz continuous, it's also alpha holder continuous. All right. Next, suppose that there exists a little lambda and a capital lambda, both positive, such that condition number one, sum over ij, aij of x, ci, cj is bigger than or equal to some lambda times the norm of the xi squared. And all of these absolute values, these are referring to Euclidean norms. Okay, so this is for all x in my domain omega, for all xi real valued vectors xi. This condition is basically the positive definite condition. It says that, right, the smallest eigenvalue has to be bigger than zero. That's another way to interpret it. So if we're talking about diffusion processes, this is satisfied a lot of the time, not all the time. Second condition, we have some kind of, so I think maybe it's good to tell you guys where I'm going with this. I'm going to write out a bunch of conditions on the data to the Poisson equation. And then I'm going to say under these conditions, we have bounds on the derivatives of the Poisson equation. Okay, we know these a priori. All we need is some kind of special conditions on the data. And the precise conditions on the data are very important because otherwise you can't really apply this theorem, which is why I am being careful here. So dxy alpha aij of x aij minus aij of y divided by x minus y power of alpha less than or equal to lambda, and some notation dxy. This is the minimum of dx and dy, and this and dx, this is the distance from the point x to the boundary of omega. Okay. So just a moment. Maybe let me call it dist, not to confuse people. Okay. So the D, I'll come back to it later, but the first condition is basically saying that the diffusion coefficient is bounded itself, right? That on this on the small set, the norm or the maximum of the diffusion coefficient is bounded by lambda, but also its derivative is bounded as well. Its derivative is alpha holder. Okay, with so lambda is serving as the upper bound. Good. That's condition number one. Condition number two, let me number these. This is 1, 2. Condition number 3, supremum of x in omega dx bi of x and supremum x comma y. And after writing these down, I will walk us through our MH2 example and see how all this works. So same thing for the diffusion, so for the drift. We have the maximum value of the drift and some kind of alpha holder constant on the drift. And we've got this extra term d sub x. Okay, and I'll again make note of what that means for us in this moment. But this basically is saying that the drift should not be growing too quickly, and its derivative should be bounded. Well, alpha holder. Next, we have our results. Then there exists some constant depending on the dimension of the problem, the alpha in the alpha holder condition, little lambda and big lambda, such that if I take my Poisson equation solution, then its value on this set plus the supremum x of omega norm b equals 1. The magnitude of the first order partial derivative is bounded plus supremum x in omega norm b equals 2. This is the second order derivatives. Plus supremum of x, y in omega, norm b equals 2. Let me just write this down here. dx comma y to the power of 2 plus alpha d beta u of x minus d beta u of y x minus alpha x minus y to the power of alpha. So this is the left-hand side of the bound. Let me copy it over to the next page. This is less than or equal to this constant, which depends only on the dimension, alpha, little lambda, big lambda, multiplied by supremum x in omega, u of x, plus supremum dx squared f of x. And remember, f is the test function in the Poisson equation. Plus supremum x, y in omega, dxy 2 plus alpha, f of x minus f of y over x minus y to the power of alpha. So this is the result. Okay, and now I'm going to make some comments. Let me know if there are questions about it. So what we have basically established, these are called a priori Schauder estimates for elliptic PDEs on, stick with that, for elliptic PDEs. And this result, if you want to prove it, you have to go into classical PDE theory. There is a very well-known textbook by Gilbert and Trudinger. And this basically covers PDE theory from, not in a non-probabilistic manner. Let's just say that. It says basically that for any Poisson equation satisfying some regularity conditions on the coefficients, the solution, its first order derivatives, all of them, its second order derivatives, all of them. And this thing I would like you to think about as almost the third derivative, right? Because again, if alpha equals 1, then this is the Lipschitz coefficient of the second derivative. But alpha is not going to be allowed to be 1, and that's crucial. But still, this is basically control on how the third derivative grows, more or less. All these first three derivatives are bounded by a constant, which it depends on the dimension, okay? And there's no way around that. It depends on the Holder coefficient. It depends on little lambda. So this is the smallest eigenvalue of the diffusion coefficient matrix. And it depends on big lambda. And I'll review what big lambda is again when we check the conditions, but big lambda is basically a bound on the drift and a bound on the diffusion coefficient and its derivatives. And it says that all of these first three derivatives of the Poisson equation solution are bounded by the Poisson equation solution itself. And here we have the test function information. So again, I would like you to think, for starters, in the case where, let's say, f is Lipschitz 1. So if f is Lipschitz 1, and suppose without loss of generality that f of 0 equals 0. Remember I showed you this. No, we can't assume that. My bad. We cannot assume that. Not in this setup. At any rate, this part grows at most linearly in x, right? So we have something that grows at most linearly in x multiplied by this distance squared. I'll talk about it in a second, but we will want to take the sets omega to be pretty small sets, pretty small balls, and they will be getting smaller and smaller as the value of x gets larger and larger. And in that case, if the balls are small, then the distance itself is going to be smaller and smaller. So the distance of any small ball to its boundary, it's going to be small. It's the radius, at most the radius, basically. And here we have, again, the Holder coefficient of the test function itself. So my point is, these two objects, we have control over them. It's for us to choose the test function f. And if f is Lipschitz 1, for instance, then this thing is going to be bounded by 1, what I've circled. Okay, so there are fairly trivial bounds on these quantity number 2 and 3. But quantity number 1, that is where all the difficulty lies. Okay, why? Well, usually, so what's special about this bound? Usually, if we know information about a function's derivatives, suppose we can bound the first derivative of a function, then we can bound the function itself, because if we know the derivative bound, then this is a bound on the rate of change, and we can have some kind of like maximal growth condition on the function. This upper bound, in some sense, it's backwards, where we have the derivatives up to the third order, and they are bounded by the function itself. Okay, so that's one distinction. And if you want to apply this result, the most difficult part to control is the solution to Poisson's equation itself. Okay? So before I talk about how we want to control the solution to Poisson's equation, let me make a few comments, an important comment about the conditions notes. And specifically, I want to talk about condition number 2, and I want to talk about condition number 3. Condition number 2 is on the value, or largest value, of the diffusion coefficient and on its growth. So first, basically, we need to assume that the matrix Aij is, this is all ij, is positive definite for all x in omega, and have bounded entries and alpha Holder constant. And the upper bound that's responsible for this is lambda. B. Typically the drift B of x is Lipschitz. And this is, when I say typically, I'm referring to, let's say, queuing applications. We're going to take a look at our example from last class, and then we're going to confirm that B is indeed Lipschitz, but typically B is Lipschitz. And what does that mean? Therefore, B of x, Bi, is bounded by, let's say, Bi of 0 plus absolute value of x. Yeah. Okay. So this is a problem. Well, it's not a problem. We just need to be careful. This is a problem here. So if the drift is Lipschitz, then the alpha Holder coefficient is bounded. That's no problem. But the drift itself grows. So as our set omega gets farther and farther from the origin, the drift will be allowed to grow at most linearly. And all up until now, we did not fix what omega is. I've been talking about generic omegas. And this is what necessitates our specific choice of omega. Okay? The fact that the drift grows. So we want to take advantage of this distance from x to the boundary of omega. And we would like this to work in our favor, to shrink or diminish this term, right? Because if this just grows unchecked, then the lambda is going to be growing and growing and growing, and then the constant in front of the upper bound is also going to be behaving in some weird way. So to make supremum of x in omega dx bi of x bounded, we select omega to be this special ball around x, where the special ball is the ball around x with radius 1 over 1 plus absolute value of x. So on a picture, what these bounds are going to look like is, let's say this is RD, R2. We have the Poisson equation, which is defined on all of R2. And in order to bound it, we're going to just focus on local neighborhoods. Instead of establishing a single global bound for the derivatives, we're going to focus on local neighborhoods of these things. That's where the omegas come in. And then you can say, okay, well, how do the omegas look like? What they're going to look like is the farther you are from the origin, the smaller the radius of the ball. And the radius of the ball shrinks in proportion to 1 over 1 plus absolute value of x. And what this allows you to do, the distance, let's say, from any point y to the ball of x, this is for all y in the ball, this is at most 1 over 1 plus, so at most the radius. Therefore, supremum x in this ball, let's dx norm bi of x is at most 1 over 1 plus absolute value of y, x plus bi of 0 for Lipschitz drift. I kind of, I'm not At the start of class, I said it won't be super duper detailed, but I guess I am being it. Let me put all the coefficient, let me put all the pieces together, okay, right now. So if we take our diffusion process, H2n plus m diffusion approximation. Okay, and just to remind you what it was dy of t. Maybe I don't even need to say that. The drift b of x, this was beta. This is the half-in-width parameter times the probability of being type 1, type 2. So this is in vector format. Minus nu, well, let me just write it beta sub I. Pi minus nu I x sub I, and aij of x. This was in matrix form, perhaps easier. Two mu plus delta beta over square root of r. Okay, so I think now that I'm going to work through the example, it'll make a lot of the pieces click, and why this theorem is so important. So let's start by looking at the diffusion. Oh, pardon me, I've forgotten the abandonment part. Plus E transpose X, positive part, nu I minus alpha multiplied by pi. There. So that is the full form of the drift. And now let's start with our diffusion process, and let's see if this result, which we just spent so much time on this theorem, is of any use to us. Okay, so the first thing is I want to verify the conditions, or I want to look at the data. Okay, so first things first, the diffusion coefficient matrix is going to be times P1, P2. Now it's a matrix. Okay, this is some positive constant, and this matrix is trivially positive definite. So this matrix is positive definite. Great. At the same time, it's also a constant matrix. So the Lipschitz, or the alpha holder constant of this diffusion coefficient, is 0 because it's a constant, or its derivative is 0. So great. So far, this satisfies our conditions. Okay, a is constant. That means it doesn't grow too much, or we can bound it by some capital lambda as well as its derivative. What about b? Well, b, if you look at it, it's Lipschitz, right? The dependence on x is at piecewise linear, which makes it Lipschitz. And that says that if we go back to our theorem over here, we're going to need to know how the drift grows, and we're going to need to know something about its Lipschitz coefficient. Okay, so the dependence on the growth of the drift, it will depend on all of the constants, and the Lipschitz coefficient will depend on the nu and this constant in front of the E transpose X plus term, right? So in other words, if I were to write C, D, alpha, lambda, capital lambda, this would be a constant which depends on the dimension. In this case, it's 2. The drift and diffusion coefficient are Lipschitz, so they are indeed C2 alpha, or they have finite or bounded alpha holder coefficients for any alpha less than 1. What is our little lambda? Well, the lambda we can infer based on the structure of the diffusion coefficient matrix. It'll depend on some beta over square root of r, mu, p1, p2. I'm not going to calculate the eigenvalue on the fly, but we just coarsely say this. And the lambda, the upper bound on the drift and diffusion coefficient growth, is going to depend on beta, pi, nu I, alpha, etc., etc. Okay, so obviously the derivatives of the Poisson equation are going to depend on these coefficients to data. The biggest downside to this theorem is if you would like to know how this constant behaves explicitly in terms of these coefficients, you're out of luck. Okay, because I think, is it theoretically possible to find all of these and to backtrack your way through this Gilbert in Schrödinger textbook? Maybe theoretically possible, but in practice, it's extremely, extremely difficult to track this constant all the way from the start. And so for our purposes, this constant is like a black box constant. We know it depends somehow on these parameters, and we don't know how exactly. So what does this tell us? Actually, this tells us something important. It says that, right, we last time were chasing a result which looked like the Wasserstein distance bound between our M to H model, our MH2 model, and the diffusion coefficient. And this thing should be bounded by some constant, say over square root of r. This was the target rate of convergence. The constant here better not depend on r, or better not grow as r grows. Otherwise, this is not a good bound, right? Well, if we want the constant not to grow as r grows, it's dangerous having the diffusion coefficient or the drift depend on this r. So if we let r go to infinity, this part of the diffusion coefficient washes out, and we're left with a constant diffusion coefficient. And now we're left with what is called the diffusion limit, right? This is what everything converges to in the half-and-width regime, and it depends on the beta, on the half-and-width parameter. And this is a single mathematical object, right? If we keep the r in the diffusion coefficient, now we have a sequence of diffusion processes which depends on r. And we will have not one constant in the Poisson equation, we'll have a sequence of Poisson equations, and we'll have a sequence of constants. And that ideally, well, not ideally, that better not depend on r. That better not grow as r grows. Okay. Now here specifically, you may be able to say, well, my condition on my lambda was that it just be an upper bound for the diffusion coefficient. And so here as r grows, we can use the same upper bound uniformly across all values of r. So this would save you. But I just want to point out that if your diffusion depends on the parameters of your prelimit fully, and not in, say, some asymptotic regime, then you got to be careful about the growth of this constant. Okay. Enough said on that. I think I've almost beaten it to death. We've talked about the result. We've talked about which are the conditions that you should pay attention to the most. We've talked about the constant not being in closed form and perhaps hopeless to have a closed form, or extremely difficult. Although with ChatGPT, I'm curious what it would say. It would probably dig through the book and maybe be able to say something. All right, we have basically at a high level a result which says that the Poisson equation solution, its first, second, and third order derivatives are bounded. And in the upper bound, I've said that we have three terms, term number one, term number two, term number three. Terms number two and three, they're simpler to bound. They're pretty simple because those depend on the data of your problem, the test function you use, which is up to you to choose. And the most difficult part is the value of the Poisson equation solution itself. So this is the final piece of the puzzle, because if you go back to our example and you apply all this technology and you pick the omega sets very carefully, and you do all these nice things, you're going to end up with this bound where the Poisson equation solution itself shows up, and you're thinking, well, how do I bound that? It's kind of like, seems like a circular argument. Let me pause and ask if there are any questions, people generally following. No answer is a good answer. Okay. So the $1,000,000 question, how to bound the Poisson equation solution in omega u of x. And we've kind of been talking about this. We've kind of given the answer already. Number one, u of x is bounded by, this is the probabilistic interpretation, norm expected value. So remember, test function f of x. You know what? No, let me switch back to our original notation. Let me switch back to our original notation because I want to start departing that result I just stated. How to bound f sub h of x. Back to our typical notation. T. Two ways I suggest doing this. Approach A. Establish exponential or sub exponential ergodicity. And this is the approach that is proposed by Tygorovich in the paper, hence the title Exponentially Ergodic Diffusions. And how do we do that? For example, suppose there exists some V, and I've said this before, it's bigger than or equal to 1, let's say, such that V of x goes to infinity as x goes to infinity. And the diffusion generator applied to this function satisfies negative C V of x plus D indicator that we're in some compact set K. K is compact. Then the process is called V exponentially ergodic. Which means for any test function h from Rd to R such that norm h over, such that the function is bounded by V. Expected value x h sub y of t minus expected value h of y is less than or equal to some c1 v of x e negative c2 t for all x in our Euclidean space. So last time I just kind of flashed the concept of exponential ergodicity. This is what we call V exponentially ergodic. So the property or the exponential convergence to stationarity, which we have over here, depends on your on your function v. On the one hand, having a large v is attractive because if v is very large, then there are a lot of test functions h for which this exponential convergence holds. On the other hand, having a large v hurts you in the upper bound because the upper bound depends on the value of v itself. And so there's this kind of trade-off. But if we have exponential ergodicity, uh, what we can conclude about the Poisson equation solution is bounded by 0 to infinity. And we just look at its form over here. And this integrand is exactly what we bounded in the exponential ergodicity condition. So we'll have C1 v of x e to the negative C2 of t dt. And this is, of course, bounded by some constant, let's say C3 v of x, because you integrate the exponential and the integral becomes finite. Okay, now I said exponential ergodicity or sub-exponential ergodicity. Sub-exponential ergodicity is basically you can have a weaker drift condition to satisfy, and you get that the convergence to stationarity is not exponentially fast, but it's guaranteed to be polynomially quick in terms of t. And that's good enough. Now, why is this a good idea? Why is path A a good idea? Because in queuing, this is like the bread and butter sometimes. If we want to establish stability or we want to establish exponential ergodicity, these Lyapunov functions are sought after in the literature, right? So there's a close connection to what queuing theorists do anyway, and how that would help give you gradient bounds on the Poisson equation solution. Now, the other way, which I think I haven't seen popularized so much, but it's a powerful way, because the downside with approach number one is that a lot of the times, and especially if the model is complicated, finding this type of Lyapunov function is very difficult, can be extremely hard. Okay, so in those cases where finding the Lyapunov function is very hard, we have approach B. And approach B, we've kind of seen it, coupling argument. Approach B basically reduces to first order bounds, derivative bounds suffice. Okay, what do I mean by that? So we take our function f sub h of x, and we look at its norm. This is what we want to bound. And now I have my expected value starting from x, and I've had the steady state expectation. Okay, so now I want to say, and I showed you this 1 or 2 lectures ago. I want to rewrite the steady state expectation as the expectation over some initial condition of the stochastic process. And I'm going to integrate over the reals of pi dy. Or let me assume everything has a density, although that's not strictly necessary. But let me assume that everything has a density. So pi sub y dy dt. And now I'm going to basically use the fact that so pi is the stationary distribution of the diffusion. This thing integrates to 1. And so I'm going to use the Fubini-Tinelli result to interchange my 2 integrals, r d. I have expected value of x, h of y of t minus expected value y, h of y of t. I have the norm here, and I've basically pulled out my expectation integral pi of y dy dt. All right, and then I will just flip or swap these two again. V and Nelly. And what I'm left with looks a lot like a first order bound. So I take my diffusion process, I started in state X. I take my another one started in state Y. And since this is a difference of two expectations, I'm free to couple these two diffusions in any way I want. And are some obvious couplings which make our life easier. So suppose we bound this integral from 0 to infinity x h of y of t minus expected value of y h of y of t dt. Suppose we can bound this. As a result, can integrate with respect to pi of y dy to bound the Poisson equation solution itself. Okay. Another similar way, maybe it's called approach B prime. If we take the Poisson equation solution and we say bound it at its value at 0 plus norm of x, say the sup of the derivative of the function 1, and this is some z, where z is between 0 and x. Okay. Roughly, so a bit hand wavy. Conceptually, these two ideas are very close, right? So here what I'm saying is if I can bound the first derivative of the function, then I can bound the function itself. Here, what I'm saying is let me bound what will look like the first derivative if x and y are close. All right. So in our example, let me just give you an idea of how difficult this is. It's not trivial. So as I said before, we have a diffusion process, diffusion limit, let's call it y of t. And I'm not going to bother with outlining its structure. We have a diffusion limit y of t. Define the synchronous coupling psi of t to have the same Brownian motion as y. But let's call it the initial condition is the same initial condition as y plus epsilon so we're perturbing it in the first direction. Let me give you the high level steps. Ideally, right, if we're looking at trying to bound this thing, ideally we have a rate of convergence to 0 of the distance or the difference of these two expectations. Ideally, we want to bound expected value, let's call it initial condition on y and initial condition on the psi, h of psi of t minus h of y of t, say less than or equal to something like c1 e to negative t c2. But problem, If we try to look at this difference directly, okay, doesn't have to decay in T. So if you remember that when we were doing the in the prelimit approach, we were doing these couplings to have derivative bounds or Stein factor bounds. And I said a very important property of this synchronous coupling is that the infinite server queue doesn't, and its copy, they don't drift apart before coming together. If you look at this diffusion process and you look at the norm or the difference between psi and y, this doesn't necessarily go like strictly decrease. Okay. And so solution, we have to do a change of variables. And I don't think I could have come up with this myself. My PhD student came up with this. So we define P1 of T, be little P1. Remember, this is just a high level idea to show you the level of complexity involved. So it's not trivial. So P1 is the probability of being a type 1 customer. So we have some linear weighting on the psi components. And the second coordinate is the sum of the two psi components. And same thing for the y's. We have Q1 of t. This is a reparameterization. Y2 of t minus P2, Y1 of t, Q2 of t. So we do a change of coordinates first. Okay, and this gives us a vector P of t or a process P of t, and this gives us a process Q of t. And not only do we have to define, not only do we have to reparameterize or do a change of coordinates, we define the omega or W norm of a process x of t sub W. This is the norm of x1, the first coordinate, plus W of the second coordinate. Okay, then we can show that P of t minus Q of t in the W norm is exponentially, well, we can satisfy d by dt is less than or equal to negative constant P minus Q omega. Therefore, and this is using Gronwall's inequality, P of t, Q of t in W is at most C1 e negative C2 t times the initial condition. Okay. So why am I showing you this? I'm showing it to you so that you can appreciate the level of difficulty here. It's not impossible, but so far this was restricted to a two-dimensional example, the H2 service time. If we generalize two types of customers to any number of customers, then the dimensionality of the diffusion grows. And honestly, I have no idea how my PhD student came up with these weights. And I can imagine that even in 3 dimension, maybe we can't find them, or maybe it's really hard, or maybe we get lucky and find some structure, whatever. You can see. And then plus the weighted norm itself. This is for some W. There exists a W. Okay. Now, on the flip side, you might say, okay, I get your idea B. I get this procedure, but is it really the right way to do it? Is this really the right path to pursue? Is it not easier to find this exponentially ergodically Lyapunov function? So for this particular model, for the m ph n plus m, finding and I was told this anecdote by the authors of the paper, but it took them, I think, 1 or 2 years to find the Lyapunov function that will satisfy this kind of exponential ergodicity condition. And even then, they had to, it's called a common quadratic Lyapunov function. So even constructing it is not trivial, let alone just explaining what it is and verifying the drift condition. So sometimes this path can take you, I don't know, a year or 2 years. Sometimes path B is, at the end of the day, simpler. But even then, you might run into a situation where even if you start two diffusion processes from the same initial condition, they'll drift apart before eventually coming back together, unless you find some clever reparameterization on which they on which in which they just come back together. Okay, so now you're armed. I think still my promise to you was kept. I could have dove into a lot more detail here. I don't feel so bad. But now you are armed with a good result, which basically says that your drift, you just have to control the Lipschitz coefficient of your drift, and you have to control how quickly your diffusion coefficient grows and its Lipschitz coefficient. And that is a fairly low bar. Like, you know it explicitly once you write down the diffusion. You know these growth coefficients right away. So using this theorem, then you can apply it to many settings. Good. Let me leave you with one last reference. And these guys do it a completely different way. Gorham and Mackey. And I will come back to this part of the notes with a precise name of the paper. Actually, let me see this. Measuring sample quality with diffusions. Let me just quickly check that it is the right paper. Yes, except I gave you the wrong authors. So this is a little bit more authors. Gorham, Duncan, Sebastian, Vollmer, and then Mackey. And I'm looking at the archive version, and the latest one is, let's say, 2018. So let's just call it 2018, measuring sample quality with diffusions. And here they have a different approach. To Stein factor balance. Okay, but it relies a lot on structure, on some assumptions of how diffusion behaves. So it is, it's restricted to a certain class of diffusions, which is different from Itai's theorem. So this is some good background for you to have, just in case you need it. All right, now I want to move past this multidimensional stuff. And before I completely switch gears and we'll talk about non-Markovian models or general models, I'm going to just pause for a couple of seconds for questions. Okay. So we have half an hour now and then 90 minutes. So we got about 2 hours left. What I want to do in these 2 hours is touch on two topics. Topic number one, which we're going to start on today. This is Stein's method for, let me use quotation marks, non-Markovian, although that's not accurate. Non-Markovian models. Really, this is models with general primitives. And then two, Stein's method for mean field models. Just to give you a roadmap of what I want to cover, when we're going to talk about models with general primitives, here we're going to be departing the typical simple queuing assumptions where we have like Poisson arrivals and then exponentially distributed service times. And I want to show you how to extend the generator approach to that setting. I'm not necessarily going to go and fully complete one example, but I want to give you the main ideas. And I want to expose you roughly to what's going on with Stein's method for mean field models. And here we have a couple of things. I think one of the research questions here is basically how accurate are mean field models? And we have accuracy guarantees like we would expect. And then we have higher order accuracy guarantees that perhaps you wouldn't expect right away. The burden of working with mean field models is a lot lower than with diffusion approximations because the mean field models are deterministic. At the same time, it's not trivial. It doesn't get trivialized by that. And here, basically, this is a recipe in queuing. This is a recipe to prove tightness. So a systematic recipe to prove tightness of a queuing system, which when combined with process level convergence, implies convergence of steady state distributions. All right. So to motivate our discussion, I would like to look at the GG1 work, and Ziv has already seen a lot of this because this is based on stuff we're working on together. Sorry, Ziv. So here I want to talk about the workload process. Okay. And what does the workload process look like? We can talk about the queue length. We can talk about anything about the GG1, but I want to start with workload because it has a fairly simple representation. Okay. So suppose I start off with some initial level of work. In the GG1 system, the workload will decrease at a unit rate. So we're assuming that if there's work in the system, the server is working. And the workload will decrease at a unit rate until the first arrival happens. So what letters do I want to use? U sub 1. Okay, so after use of 1 time units, a customer arrives into the system. The first arrival happens, and there's a jump because the first customer brings in S1 work into the system. So S is for service. And then the server keeps going. The second arrival happens, and perhaps it's better to show you that the inter-arrival times are U. And now this is, again, we jump up by S2, and then the server works. Nobody shows up. The system becomes empty. The server idles, and then a third arrival happens, U sub 3, and then the system jumps up again, and we keep going. S3 or E. Okay, so this is the workload process that I want to understand. So we have UI, or IID, according to some distribution U. We have SI, or IID, according to some distribution S. And we have V of t. This is the workload, or virtual waiting time, it's also called. Workload at time t greater than or equal to 0. And I'm going to let delta, the scaling constant, be 1 minus rho, where we have lambda. This is the arrival rate. So lambda, this is 1 over the expected inter-arrival distribution. Rho, this is lambda times the expected value of the service time duration. And delta, this is 1 minus rho. And x of t, I like using x for always the quantity we're actually going to work with. This is going to be a scaling of the workload. There's no centering. The centering is around 0. Okay, so let's not make any more assumptions than we need to. We'll see what needs to happen as we go along. And first things first, I want to talk about what is the state descriptor. So I would like a Markovian state descriptor. If I look at the workload, so maybe let me write x. So everyone agrees, I hope, that x of t and v of t contain the same information. One is just a rescaling of another. If I look exclusively at the workload in the system, is this a Markovian? Is this a memoryless? Does this satisfy the memoryless property? No, it doesn't, right? Even though we know that this thing is going to decay at a constant rate, we don't know how long it's been since the last arrival. So we need to know not only the workload in the system, but also some information about the time since the last arrival, or how much longer until the next arrival. So there are two descriptors we could use. We could look at the workload in the system. Maybe let me not use A, let me use alpha. And alpha, A, is the age since last arrival. Okay, this is when was the last arrival, or this is called the backward recurrence time in the renewal process language. Or a second state descriptor is x of t and the residual arrival time, Ra of t. This is residual inter-arrival time, which tells you basically how much longer until the next arrival happens. And if we look at this picture here, and if I pick any point on the graph, so let me pick the point over here. And suppose I know the workload, and suppose I know the residual arrival time or inter-arrival time, then I know the dynamics of the process, because I've got my workload, which is going to keep decaying at a constant rate until the server finishes all the work. And until the next arrival, my process is fully known to me, right? In fact, it's deterministic until the next arrival. The next arrival happens at this instant. It introduces some work into the system. The amount of work introduced, it's random. It's a random variable, right? So if I ignore the if I ignore the arrival events, my process is deterministic. And this is called a piecewise deterministic process. Okay, or PDMP. So this piecewise deterministic Markov processes are a generalization. There's a paper by Mark Davis in 1984. These are generalizations of continuous time Markov chains to models where the inter-arrival distributions, let's say, are no longer exponentially distributed. Okay, and a quick word, what happens when everything is exponential? So really what needs to happen is for the inter-arrival distributions to be exponential, and then we no longer need the residual inter-arrival time anymore, right? Because if the inter-arrival distributions are exponential, then the time until the next arrival is always going to be exponentially distributed. So here I want to introduce a concept or just some terminology. I'm going to call this a general clock. I'm going to call the residual interarrival time a general clock because this is coming at this from like a simulation perspective. If you want to simulate the behavior of the system, then you simulate the value, or you initialize a certain value for the residual arrival. And then this is like a clock that keeps ticking down. And when it hits zero, an arrival happens and your workload jumps. Now, I guess, yeah. You may ask, what is the difference between these two representations? Representation number one, representation number two. Are they equivalent? And I'm going to say no. Actually, representation number two is a bit more general. Why? So if you imagine having, and I'm not going to prove this, but if you want your age and workload to be the state descriptor, then what you're basically doing, and this is the way that Davis initially did it in 1984, what you want to happen is you're tracking how long it's been since the last arrival, and you're basically using the hazard rate of the inter-arrival distribution as quite literally in the sense of how much longer, what is the probability of us surviving an extra instant of time given we've survived this long already. So in order to have this be a Markovian state descriptor, we need hazard rate. What does that mean? It means that the inter-arrival time distribution, should have a density or should have a hazard rate. Okay. And if, for example, u is a discrete random variable, then we need to use, instead of hazard rates, we need to work with the residual times. So the difference is that the residual times can cover inter-arrival distributions with point masses. Okay, so this is just for generality. But if you're curious, I think if it's easier to work with the ages, then perhaps it's a good idea to start with them too. Good. So what are we after? We are after a method, or we are after extending the generator approach to this piecewise deterministic process. And I'm going to call this tuple. I'm going to use Z to denote the entire process. Z of t. This is x of t, comma, residual arrival time. All right. And in the last 10 minutes, what I want to do is I would like you to appreciate the fact that just using the typical generator comparison approach here doesn't work, or something needs to be done to it. Okay, so let's try to apply generator comparison. And we define the generator with respect to the workload process, which has two components to it, the workload and the residual arrival time. And we define this as the limit as t goes to 0, expected value sub z, f of z of t minus your initial condition over t. Okay, now I want to be a little careful with the state space. So I want to take z, this is x, r, a, Now, what is the state space allowed to be? The workload can be non-negative, but the residual arrival time, let me just look at the picture I drew. I drew this process as being right continuous with left limits. Okay, so the residual arrival time, it also decays. It hits zero exactly when the process, when an arrival happens. But notice here the workload jumps right when the arrival time was supposed to be zero. In other words, because we have adopted for the right continuous version of the process, the state x comma 0 is technically never visited by z of t because it is right continuous with left limits. But okay, I'll come back to that point. So suppose I have some non-negative workload and I have some residual interarrival left that's strictly positive, and I try to compute this limit, e sub z f of z of t minus f of z over t. Here I want to use the structure of my piecewise deterministic Markov process, right? Basically, as long as this time is not very far ahead into the future, my process behavior should be deterministic up until that point of time. So we take, and how long, what do I mean by not too far ahead into the future? I take t to be smaller than the residual arrival time. And then we know that from time 0 until time t, we have the following behavior. We have deterministic behavior. An expected value starting from 0, f of z of t. This is basically f. I look at my workload, x. I subtract. So over time from 0 to t, how much of the workload is drained? Delta t. Remember, x is the scaled workload. And so we drain delta t work. And of course, this cannot be negative. So we take the positive part. So if we run out of workload for any reason, right, we want the positive part. The server just idles. The work in the system doesn't become negative. For simplicity, if this is your first time seeing this, you can imagine that x is strictly positive, in which case for t small enough, this part will not be negative, right? And then we have residual arrival minus t. Therefore, coming back to the generator, this is f of x minus delta t plus residual arrival minus t minus f of z over t. And now we split into two cases. Case 1, x is bigger than 0. If x is bigger than 0, I get f of x minus delta t for t smaller than x over delta, comma r a minus t minus f of x r a over t. Just copy this over. Okay, and this now, provided the function, let's say, is continuously differentiable, and you look at the difference, and as t goes to 0, this is just the derivative. And so here it converges to, we have the first order partial derivative, or the derivative with respect to x of f of z, and the workload decays at rate delta. And we have the derivative with respect to the arrival, inter-arrival time. And that's it. If we have case 2, x equals 0, basically it's a lot simpler. And we have f of 0 minus delta t, positive part, comma, ra minus t, or minus f of 0 ra. So the server is already idling. And then this equals, there is no change with respect to the first coordinate, and there is a change with respect to the second coordinate. Therefore, for any point not on the boundary, the generator of a function is, so we go with this is the first component. As long as x is positive, we have the first derivative active, and then the derivative with respect to the second component is always active. And I'm just going to leave you with a question to prompt the further development of this. I've derived here the generator. We've all seen it. I went into full detail. There were no tricks up my sleeve. Usually we're used to the generator encoding everything about the behavior of the process, right? The generator contains everything. But here, where is the information about the service time? I can kind of believe that the inter-arrival distribution maybe somehow is contained in this term. Although, right, if f is just any function, let's say f of x is the identity function, there is nothing random about the derivative with respect to RA, right? So there's nothing random here. This part kind of reflects the piecewise deterministic structure. Where is the randomness? And this is the question we're going to answer next time. We're going to start with that. And it turns out that the randomness is hidden on the boundary here. And therefore, the definition, and I'll show you why, the definition of this generator, as we are used to it, it kind of doesn't work for this process unless we're talking about some very special functions which satisfy a certain boundary condition. Okay, so we need to, instead of doing generator comparison now, we need to go one step higher and we need to look at the BAR for the process. So we need to compare the BAR of this to its diffusion. So that'll be the topic of next class. Probably spend about an hour on that. All right, thanks everyone. See you in our final lecture.
Thanks, everyone. Any questions for Anton before we end?
Okay, so there's a good question here. For GG1, what is the advantage over this model over Lindley's equation? So I want to talk about maybe the right answer here is Lindley's equation is special. It's you get lucky. Very special structure restricted to the one-dimensional waiting time. If you want to talk about models which extend beyond GG1, like many server system with general arrivals, you no longer even have a Lindley recursion, right there. So Lindley's equation is only GG1. The other piece of the puzzle is that Lindley's equation is for the waiting time at customer arrival. So that's a discrete time model. It looks at the waiting time at epochs of arrivals, whereas the workload here looks at basically the waiting time averaged. If we talk about steady state, it's the time average waiting time. So it's apples and oranges, but in practice, you will not have the equivalent of Lindley's equation when you go beyond GG1. All right, I'm going to upload the notes and see you all on Thursday.